So today we're going to be learning about addition reactions. These in many ways can be thought of as the reverse of elimination. To that end, we just need to review alkenes a little bit. Because the alkenes are going to be the substrates. So, reviewing naming alkenes, their nomenclature. The first thing you need to do is identify the parent chain. That should include the carbon-carbon double bond. Next, you're going to identify and name the substituents, just as you have in the past. Step 3 is locants and prefixes for each substituent. You want to give the CC double bond the lowest number possible, but there's a caveat here. And that caveat is you still want to have the longest backbone possible. In other words, don't start number 1 where the alkene is located and end up truncating your carbon-carbon chain. For instance, with this compound, you may be tempted to start here, and that gives you an isopropyl group attached to a 1-butene. But, as you can see, that actually shortens our carbon-carbon chain, which really can extend to here. Step 4, list the numbered substituents before the parent name in alphabetical order. Ignore prefixes on those substituents unless the prefix is iso when you're doing the alphabetical ordering. Step number 5 is to place the CC double bond locant either just before the parent name or just before the -ene suffix. Okay, so let's do an example. So here we go. This compound is from exam 2. And we're going to name it, but we're going to ignore stereochemistry for now. So first, we need to pick out the parent chain. That's the longest carbon-carbon chain that includes the double bond. And there we go. Now, what a lot of you did on the exam, a mistake that a lot of you made, was instead of starting at the very end, you began at the double bond like this, right? And what you did was you ended up truncating your carbon-carbon chain. You want the longest carbon-carbon chain possible. That includes the double bond. And even though you want to have the double bond get the lowest locant possible, that's more a matter of which side you start numbering from, right? So clearly in this case, you'd want to go 1, 2, 3, 4, 5, 6, 7, okay? So the parent chain is going to be 3-heptene or hept3-ene. Either one is an acceptable way to end your name. Now let's look at the substituents we have. There's a methyl group here and here. So 2,4-dimethyl. There's a bromo group here, so it's going to be 3-bromo. On carbon 6, there's a methoxy, So we're going to have 6-methoxy in the name. So now what I want to do is assemble all of the substituents alphabetically. I'm going to start with bromo. 3-bromo, 6-methoxy, because O comes before Y, 2,4-dimethyl hept 3-ene. There's also another acceptable way to name it, and that is to end with 3-heptene instead of hept 3-ene, and that would look like this. 3-bromo, 6-methoxy, 2,4-dimethyl 3-heptene. Now, it should be noted that so far we have ignored stereochemistry. Now let's deal with the stereochemistry. So when we're talking about stereoisomerism in alkenes, it's all about the position of substituents on either side of the double bond. Okay? They can be Z or E. Z is like cis. Stands for together, like you see in this picture here. Okay. E is more like trans, which means separate. So if the amine group was switched positions with the H group here, that would be E instead of Z. Okay. Right now, what's pictured here is a Z configuration. Okay. And as far as priority goes, use the Kohn-Ingold system. The same way you would for S and R. Okay. So the Kohn-Ingold prelog system for assigning priority, go by whatever has the highest atomic number that has the highest priority. In the case where you have 2 carbons to differentiate between, then go to the next level. So in other words, if you have 2 groups with the same Z values, if the atomic numbers are equal, then go to the next layer. That is, whatever each one of those things is bonded to. So if we wanted to name the compound that's pictured here, we've got 1, 2, 3, 4 carbons. So it's a butene, it's a 1-butene, right? And we have an amino group and a fluoro group. And so we call this 1 amino, and of course you need a dash, 2 fluoro, 1 butene, and it's the Z isomer. So out in front, you put the Z in parentheses to indicate that both the fluorine and the amino group are on the same side of the double bond as opposed to opposite sides. So in the compound that we've been looking at from the test, our 3-bromo 6-methoxy 2,4-dimethyl hept 3-ene, there's a double bond, and we need to classify that as to whether it is Z or E. So we need to prioritize the groups. On the left-hand carbon, over here, there are 2 groups. There's the isopropyl group, and the bromo group. So as far as atomic number, bromine has a higher atomic number than carbon, so it's bromine that is the higher priority. On the right-hand side, it's really easy to see. Is it the methyl group or this whole giant thing? And it's easy to see that this one takes the higher priority. Now notice that those two groups are trans to each other, so the stereochemistry around the double bond is E. Right? Because those are our two highest priority groups. So we would need to put an E in parentheses in front of our name. Now, there is one other thing we need to look at, and that is the chirality center. Carbon 6 is a chirality center, which can either be S or R. So we have to decide. First thing, let's figure out where the lowest priority group is. That's a hydrogen which is not pictured, and it'll be on a wedge, right? Because any chirality center has two flat bonds that are in the plane, and then it has a dash which is going away from you, and then a wedge which is coming toward you. Since the hydrogen wasn't pictured, we assume it's on the wedge because everything else is accounted for. So now we prioritize the groups using the Kahn-Ingold pre-log system, and the methoxy group is first, so I'll call it A. Then this carbon over here, I will call it B. Then this one, that's C. So those groups proceed counterclockwise. Okay. Now, counterclockwise by itself isn't all the information we need. We also need to know whether the highest priority group is pointing away from us or toward us. Since it's on a wedge, it's toward us. Right? That means that the chirality center is in the R configuration. Okay? If the hydrogen happened to be pointing away from us and we had counterclockwise, it would be S. But it's R. Okay? That means that our stereochemical designation at the front of the molecule isn't just E. We need to put in E and R. Now our name is complete. And note that if we had multiple chirality centers or multiple double bonds with different stereochemistries, we would need to number the E's and the Z's and the S's and the R's. But in this case, there's only one double bond and only one chirality center, so it's obvious what we're referring to.